Okay, so we took a look at an experiment and we saw or looked at how force, mass, and acceleration, these three concepts, force, mass, and acceleration, how they all kind of influence one another. And these three things will come together to give us Newton's second law, which is what we're going to talk about in this segment. So Newton's second law, from our little experiment, we saw that a force causes an object to accelerate. So force causes acceleration, and the acceleration is directly proportional, meaning that if I increase it, it's directly proportional to the force. So more force causes more acceleration. But it's inversely proportional to the mass. More mass, less acceleration. And if we relate all these together, we actually get a very simple equation of acceleration is the force divided by the mass of an object. As we can see, there are little arrows over the top of force and acceleration, indicating that they are vector quantities, meaning that they have both magnitude and direction. And we saw this last unit when we talked about acceleration and velocity, because those also both have both magnitude and direction. So the direction of the acceleration indicates the direction that it's not just necessarily speeding up or slowing down, but the positive and negative direction as well, just as it did last unit. So Newton's second law actually is slightly more complex, in that really not more complex, but it just adds this F net thing. And a net force is the sum of all the forces of an object acting together. So in the very early part of this chapter, we talked about how multiple forces can be acting, but there can only be one net force because there's only one direction of acceleration. So even if I have multiple forces acting on an object, the net force is the sum, it's the vector sum, so the direction does matter, of all the forces acting on the object. And the acceleration points in the same direction as the net force. Now, one of the misconceptions is that the acceleration then is the direction of motion, or the force is the direction of motion, and that's not true at all. It's just the direction of the acceleration. So anytime we have something like friction acting on an object, friction opposes motion, and the net force and the acceleration point in the opposite direction of friction. And we'll examine those problems a little bit more later. So we have just a couple quick checks. And first one, it says a constant force causes an object to accelerate at 4 meters per second squared. What if I double the mass? Well, according to my formula, we know that acceleration equals the force divided by the mass. So if I double the mass, I am going to halve the acceleration, because those two things are inversely proportional to one another. Therefore, I will have an acceleration of only 2 meters per second squared instead of the original 4. A quick little conceptual example: if I have a basketball is released from rest, and this is another perfect example of when we have two forces acting on an object, but there can be only one net force. So a basketball is released from rest, and there's a stiff breeze directed to the right. In which direction does the basketball accelerate? Well, we know that there's a weight force, and that's going to cause the basketball to go straight down. But if there's a stiff breeze, we can kind of think, some of you might think of it as like a thrust or some other type of force, a general force, but technically it falls into the category of a drag force, and the drag force is pushing it to the right, which means that the object itself has a force going to the right and going down, so the resultant will be down and to the right. And we see that over on the right side, where we add these two together and we come up with a net force. And the net force is always in the same direction as the acceleration. Now, if I'm just releasing the basketball from rest, this also is the same direction of motion. But if I were to throw the basketball up from the ground, it would give me the exact same net force that I had initially, except now it's going up. So it's actually in a different direction from the motion. All right, just another quick check. It's a 40-car train travels along a straight track at 40 miles an hour, indicating that it is a constant velocity, and a skier speeds up as she goes or skis down the hill. In which case is the net force, so the net force greater? And our instinct is to say it's the 40 kilogram train car, or the 40 car train car, because it's such a large mass that it has to have a large force. But net force, we talked about with Newton's second law, a net force causes acceleration. So this 40 car train is going at a constant 40 miles an hour. So this is actually constant right here, which means that if I have constant velocity, acceleration is 0. And therefore, the net force is also 0. So with those two things in mind, the skier is speeding up as she goes downhill. Therefore, the skier has the greater net force. We have another quick check. An object on a rope is lowered at a constant speed. Well, if I'm thinking about that, if it's going at a constant speed, that means the net force is 0 and the acceleration is 0, which means that no force is bigger than the other one. So there is a weight force going down and there's a tension force going up. And if there's no net force, these two have to be equal to one another. So therefore, the rope tension has to equal the object's weight. All right, so going back to our equation, we got this equation of the acceleration of an object is equal to its net force divided by its mass. And we know that acceleration and net force are both vector quantities. And no surprise, the dude who came up with all these laws, Sir Isaac Newton, named the units of force after himself. So this net force, the unit for it is a Newton. And if I look at what my Newton is, it's what causes 1 kilogram of mass to accelerate 1 meter per second squared. So we know acceleration is meters per second squared from the last unit. So 1 Newton is equal to 1 kilogram meter per second squared, as we can see from this equation right here. So we use Newtons anytime that we talk about force. That is the unit for force. Okay, and now we have come to our first partner problem, where we're going to be trying to use our equation. Acceleration is the net force divided by the mass. And I'm going to ask you to try to set up this problem, and we'll take a look at it back in class. So as I read through it, I'm going to help you identify some things, but then we are actually going to solve this, or you're going to try to solve this problem, and we'll talk about it during class. So we have a Boeing 737, which is a short-range jet with a mass of 51,000 kilograms. It's at rest. So the pilot turns on the pair of jet engines, and we got to be careful there because it does say pair, which indicates that there are 2 jet engines, and that'll come into play a little bit later, to full throttle, and the thrust accelerates the plane down the runway. After traveling 940 meters, the plane reaches its takeoff speed or velocity of 70 meters per second, and it leaves the ground. And we're wondering, what is the thrust? That's our question, is what is the thrust of each engine? So the thrust will be the force that it is exerting to get it down the runway. So I do have a little summary of that right at the bottom here. I do have your known variables, your xi, your xf, or aka your delta x, vi and vf, and my goal is I'm trying to find a, the acceleration in the x direction, and the net force. So just a little hint, because it's a pair of jet engines, I'm going to take the actual net force that I solved for, and I'm going to go ahead and divide that by 2, and that'll be the thrust of each engine. So take a look at that problem, see if you can set it up and solve it, and we'll take a look at it during class. And that will actually conclude this section for us.